Hey everybody, Dr. A here, and in this video we are going to be discussing axial deformation due to thermal effects. So when we talk about thermal effects, we're talking about a change in temperature. So let's write that down. A change in temperature causes axial deformations, okay? And so for linear elastic homogeneous isotropic materials, with length L, we have delta equals alpha times capital delta T times L. Okay, so what are these terms? Well, alpha is what we call the coefficient of thermal deformation. Sometimes it's called the coefficient of thermal expansion. Delta T is the change in temperature, and L is going to be the member length. Okay, and so this is a basic formula. So you just multiply these three values together for a given length with all constant properties, and you will get this thermal deformation. This is axial elongation or contraction. Axial deformation due to the member being subject to a change in temperature only. So notice that this particular formula does not have any applied forces built into it. This is due to only a change in temperature. Another couple of comments I want to make about this before the conclusion of this video is that this coefficient of thermal deformation, alpha, it has units of strain over temperature, degrees temperature, okay? So that would be like 1 over degrees Fahrenheit or 1 over degrees Celsius. So if you see like a reciprocal temperature value, that's the units of alpha, okay? Now, you can, explore an integral version of this. That's not like against any rules. If you have a varying alpha value if you have a material that has a varying coefficient of thermal deformation, or you have a varying temperature, you could see an integral form of this. I'll just kind of write that down. You could have the integral, try to spell right, form is delta equals integral from 0 to L, alpha is a function of x, and then, of course, delta t is a function of x dx. So, you could see that, but, often you're not going to see a coefficient of thermal deformation gradient, or you could see a temperature gradient, I suppose. So that happens sometimes. So, this integral form exists, but it's not very common. You're more often going to see it as a segmented, expression with constant values. So that brings me to the next form, the segmented version is delta equals I from 1 to n of alpha delta t L all sub I. So if you have like segmented bars with multiple segments that each have constant properties, then you can use this summation version of the equation. And then the last form of this that I like to touch on is if a system is subject to temp changes and applied loads, we can write little delta equals the integral as I goes from 1 to n of PL over AE sub I plus the summation as I goes from 1 to n of alpha delta T L sub I. So what this larger formula accounts for is if you have a segmented axially loaded system and you have applied loads that are causing deformations and you have changes in temperature that are causing deformations on the same system, you can add these terms up and that will give you an axial deformation due to both applied loading and changes in temperature. So that's kind of a more robust version of axial deformation, kind of balled up into one big honking formula. So that's our summary of thermal axial thermal deformations, and that's going to conclude this video. Please hit like and subscribe, and be on the lookout for some examples for this material as well. Thanks for watching.